Okay, and the other thing with the, this percentage thing over here, right? See right here? You got a, unpolarized light here, and they're going up, right? They both go through a vertically polarized polarizer, and so they come out, parallel to that. They're all vertical coming out. You can see they go down 50%, 200 down to 100, right? 200 down to 100, right? But this guy, this 100 watts of stuff goes through this one. It's 90 degrees offset, right? And nothing comes out, right? So, okay, so what? That sounds good. But over here, you got the same 100 watts, right? The same 100 watts. And you put it through this 22.5 degree difference of this, right? And you get out 85 watts. And then you can put that through a 45 degree angle, which would be another 22.5 degrees difference of this, right? And again, you get 85% coming out, which would be that about 75 watts. And then you can put, see, these are both the 90, because this is 90 degrees off from the first one, you know what I mean? But it's only 45 degrees off from this one, right? From this one to this one. So it gets 50%, which is 35. So it still has light coming out all through after all these filters. And this one doesn't have one here. The first thing is, they're so disingenuous about the fact that there is light coming out of this filter here. See here, it's right here. And then they act like, and we didn't do anything to it. All we did was put this filter in here. They always do that. They're like, we didn't do anything to the double slit experiment. All we did was block off one of the slits. But we didn't, by detecting what was going through it, that's how we detected it. We blocked it off. And then it changed from a double slit to a single slit. We're dumbfounded. We don't know what's going on here. Stop screwing with stuff and then saying you ain't screwing with it. Okay? We know from previous videos that when this goes through here, all of the light, when it comes through here, all of the light it's unpolarized. That means there's just as much, like the same percentage of photons that have their E field on this axis, the same percentage on this axis, same percentage. Every axis has the same percentage. So, you know what I mean? But when they come through, they all get reoriented. Everyone gets through. Everyone except for the 90 degree. 89.99999% degrees, yeah, some of them get through, according to this probability chart, okay? So the ones that do get, all the ones that do a little percentage of this, a little percentage of that, a little percentage of that, you know what I mean? More up here, right, obviously, more these get in than someone that's, down here. So 50% get through, but all of them, 100% of them are now up and down. They have a vertical, their E field is oscillating in this vertical axis, right? Same way over here, right? But when you put it through this next one, right, over here, you're 90 degrees offset. Your photons are vertical, oscillating like this, and the wires inside the polarizer are parallel to this photon, meaning you are inducing a current. You are getting absorbed and inducing a current. You know what I mean? So 100% if you got out of the way. Why did these ones go through this and then go through this 90 and you still have stuff? Because each time you're rotating, they act like they're not doing. When you put the 22.5 degree polarizer in there, you have screwed with the light. You have taken all the vertical light and you have the stuff that got through, right? The 85% that got through. You rotated all of them, 100% of them, to be at this angle, right? 22.5. Then when you put it through this one, you changed all this light so that it is now rotated this way. And when you put it through this one, you rotated it this way, okay? It's not magic, okay? When you put these things in here, you're rotating the light that comes in, that comes out, is going to be rotated according to this. It's going to go in like vertical, but it's going to come out at a 22. Here it's going into a 22, it's coming out at a 45, etc., etc. Why are they making it into magic? And what's funny is this same exact thing is how antennas work, because a polarizer, as we have discussed, is an antenna. And nobody bats an eye about this happening, that you lose your signal, like this with your antennas with a radio station and a radio, right? And this same exact thing happens when these are all antennas for a radio, right? But nobody says it's magic. Only if your polarizer is plastic, then it's magic, I guess. Then the leprechauns come out and do stuff, I guess. The E field and the B field are rotating these photons. They know it, right? Because they tell us. They say, oh, it comes out of here, now it's all this way. Oh, and when it comes out of here, now it's all this way. So, and when it comes out of here, it's all this way. So they know what's funny is they're telling you that they rotate it with these, and then they're telling you they ain't doing nothing to the photons. So it's all magic. Like, right to your face, and you're all clapping your hands. Oh, good job, physicist. Good job, woke physicist. So all we got is the B field. What you need to remember over here, right, is that every degree of freedom other than 90 degrees has a probability of passing through the filter, right? Here's your degrees. Here's your percentages that are in decimal form. Remember how your polarizer has a transmission axis that has this arrow here, but the wires, right, are orthogonal, right? They're at 90-degree angles, right? So when you have a photon, here's a red photon with this red E field, right? The E field is red, which I don't like. He comes in, right? He's oscillating vertically, and the wire is horizontal like this black line. It cannot induce a current. It's at 90 degrees, you get nothing. You get zero. It just either passes through or it gets absorbed and then re-emitted on the other side, like if it came in right here. So no current means no E field and no B field, but no torque in this wire. It just stays black instead of turning it red like over here. Now if it comes in and your E field is horizontal, right, you can see it's horizontal to the E field down here, right, the wires, then it can induce a E field. He can induce a E field, a current in the horizontal wires, right? See, this induces a B field, right, the blue part. But look at the B field. It's lined up already with the 90-degree. They're perfectly meshed up, right? So there's no torque involved, right? There's no torque at all. This guy gets absorbed, right? The photon in the wires down here, right? They oscillate, and that oscillation either creates another photon that is thrown back out in the same direction. Like if the photon came in this way, it would be thrown out that way. But the photons are coming in straight, so they get thrown out straight. They don't pass through the filter. And some of them are just absorbed from and used as heat. But what happens when it's diagonal? What happens when the E field on the photon is oscillating in a diagonal compared to this transmission axis? See, this is the thing. Look at here. The electrons can move back and forth through this wire, right? Or if it's the polyvinyl iodide stuff that they have, polymer. Either way, you can induce the electron can move back and forth if you induce a current, right? Because this is you. Okay, you got your photon oscillating this way, so you can make the wire electron go back and forth this way. But the thing is and here when you're going up and down, you induce nothing but no torque. And here you have a great, B field you're making, right? Being horizontal with your E field, but there's no torque because the E fields and the B fields are lined up the same way. No torque. That's the difference between being diagonal and being horizontal and up and down. Because up and down, there's no fields. Horizontal, you have fields, but they're the same fields, so they give you no torque. Neither one of these give you torque. Down here, where you're diagonal, you get torque. That's the difference. And where does the torque come from? The B field, right? The B field, this here, right, induces the E field, right? Because now, see, if you're not totally horizontal, then that energy is just worthless when you're talking about an analyzer that is vertical, right? So now you only care about your, force that you have in the vertical direction, right? The stuff in the horizontal doesn't matter. And you can see when you're this way, most of your vector is towards the vertical. When you're this way, most of it's towards the horizontal. And this induces the E field in this, but that in turn induces a B field, right? And that B field is what gives the torque to turn these, to rotate these, right? And here you get more jiggling because your E field is closer to this, you know, most of its energy is already vertical. Down here, you're none of your oscillation is in the vertical. So none of it's going to be, you know, at 90 you get 0, at 89 degrees you're barely going to get any kind of oscillation. And you don't have enough to do the horizontal, and there's only two choices you got. If you can't do the horizontal, it has to go in the vertical way. Right? Let's say you're at 89.999 degrees, right? So you go through this polarizer. You have to have at least that much energy when you were at 90 degrees. If you're even slightly smaller than that 90 degrees, you do not have enough energy to induce a current for the electron to jump from one iodide to the other iodide to the other iodide, or through these, you know, from atom to atom in this metal, right? Depending on your polarizer, whether it's metal wires or the polyvinyl stuff. But you're coming in diagonal, like here, right? You're still passing along energy, right? You still are oscillating the E field. You still transmit energy to the polarizer, right? But even if you have 89.999, it's not enough energy for it to make it go from atom to atom, right? So where's that energy going to go? It'll make it jiggle vertically. Why doesn't it try to line up? Because it's supposed to line up with this E field, right? It's supposed to oscillate wherever. If this E field is oscillating this way, then this should be, you know, the electron should be going in that direction. It can't. It's not just floating there, that electron inside the the polarizer. No, it's connected to atoms. And these atoms have forces of their own because they're made of protons and electrons, which both have fields, okay? Magnetic fields and electric fields. You can jump it up and down, but you can't take it a diagonal. It just doesn't work that way. These fields here and all the electrons around ain't going to let it go in a diagonal direction. It's got to go up and down. That's why there's only one flavor when it comes to this jiggling, okay? Because when you go in this way, there's no current. When you go in this way, you're not jiggling it, you're making a current. And when it goes diagonal, yeah, it jiggles in one direction and one direction only. Even if you're like this or if you're like this, it don't matter. It'll still jiggle in a vertical up and down motion when it comes to this, okay? See, in this, the jiggling, right, so it jiggles the B field, right? So when you jiggle this, right, you're jiggling this up and down. You induce a jiggling, right? But you also induce a jiggling in the B field, right? Because it's still jiggling, right? You are also jiggling the B field in the wires of this polarizer, right? The most when you're close, right? When you're close to the vertical, right? It's the most. It jiggles at the most. Here, when it's like almost 90 degrees, it doesn't jiggle it as much, right? It doesn't transmit as much power because it has to transmit it to the vertical direction. And if it's, you know, at 90 degrees, it can't transmit any of that energy. But if it's 89.999, it can do a little bit, you know what I mean? Because it's not in. This is what induces the E field in here, and that's what induces the B field, right? So if this can only translate a little bit of its vertical E field to this is just going to induce a little tiny oscillation, right? Which means it's going to make a tiny B field. This up here, it's, you know, a lot of its power is vertical. Most of it is not horizontal. Most of it will translate to here, right? It won't be enough, you know, to make induce a current going, you know, horizontal in it.